For billions of years, the moon has been Earth's steadfast companion, influencing tides, stabilizing our planet's axial tilt, and illuminating our nocturnal skies. But what if, in an instant, the moon were replaced by a black hole of identical mass? How would this cosmic swap impact our planet and daily lives? Let's embark on this thought experiment to uncover the potential consequences. At first glance, the idea of a black hole orbiting Earth might evoke images of catastrophic destruction. However, if this black hole possessed the same mass as our moon, the gravitational pull it exerts on Earth would remain unchanged. This means our planet's orbit and the rhythmic ebb and flow of ocean tides would continue as they currently do. Gravitationally speaking, whether an object's mass is spread out, as with the moon, or concentrated into a singularity, as with a black hole, the force it exerts at a distance remains consistent. Therefore, from a gravitational standpoint, Earth's dynamics would experience minimal disruption. The most immediate and noticeable change would be the absence of moonlight. The moon serves as a reflector of sunlight, casting a gentle glow during nighttime. Replacing it with a black hole, which emits no light, would plunge our nights into deeper darkness. This lack of natural illumination could have cascading effects on nocturnal wildlife, many of whom rely on moonlight for navigation, hunting, and mating behaviors. Similarly, human activities that depend on lunar light, such as nighttime agriculture or maritime navigation, would face challenges. A black hole with the mass of the moon would be incredibly small. Its event horizon, the boundary beyond which nothing can escape, would span approximately 0.1 millimeters in diameter, comparable to the thickness of a human hair. This minuscule size means it wouldn't visibly obscure the sun during solar eclipses. Black holes are theorized to emit Hawking radiation, a form of thermal radiation arising from quantum effects near the event horizon. This radiation causes black holes to lose mass over time, a process known as black hole evaporation. However, the rate of this evaporation is inversely proportional to the mass of the black hole. Given that our hypothetical lunar mass black hole is relatively massive compared to microblack holes, its evaporation would occur over an incredibly long timescale, far exceeding the current age of the universe. Therefore, any mass loss due to Hawking radiation would be negligible on human timescales. While the black hole's gravitational pull on Earth would mirror that of the moon, its compact nature could pose unique challenges. Spacecraft or meteoroids passing close to this tiny yet massive object could experience significant gravitational effects, potentially altering their trajectories. Moreover, if any matter were to come within this minuscule event horizon, it would be accreted, adding to the black hole's mass. However, given its small size and the vastness of space, such interactions would be exceedingly rare. Beyond the physical and environmental changes, the absence of the moon would have profound psychological and cultural implications. Throughout history, the moon has been a source of inspiration for art, literature, and mythology. Its phases have guided calendars, agricultural practices, and rituals. A night sky without the moon would represent a significant shift in the human experience, potentially impacting cultural traditions and our collective connection to the cosmos. In summary, replacing the moon with a black hole of equivalent mass would leave Earth's gravitational dynamics largely unaltered. However, the absence of moonlight would darken our nights, potentially impacting both natural ecosystems and human activities. This thought experiment highlights the intricate balance of celestial relationships and how even subtle changes can have profound effects on our planet and society.